All right, chapter 12, we're going to talk about kinetic energy of rotation and torque. If we have something moving in a straight line, we already learned that it has energy, and that energy can be used to do work. And that kinetic energy is just 1/2 mv squared, or its velocity is in a straight line. But what if something is spinning like a disk? Well, we realize when something's spinning, it's not just what mass it has, but the mass, how the mass is distributed, or essentially the moment of inertia, is what matters more than just the mass. And v varies, like in a spinning disk, the velocity on the inside is much slower than the velocity on the outside. And so this doesn't translate well, so what we need to do is we change our variables. So the kinetic energy of rotation actually becomes 1/2 I omega squared. Now remember, I is mass times kilograms meter squared, so it's the mass times the distance squared. But omega squared, omega is equal to v over r, so the extra meter squared you get there cancels out from the meter squared here if you replace it. So that actually is equivalent to that. They both are in joules. It's just this is kinetic energy of rotation, this is kinetic energy of translation. All right, so keep that in mind when you're doing energy and you're rotating something. You have to take into account the energy of rotation. We still use that energy is conserved. Energy initial equals energy final. It's just if you have something spinning to begin with, it would be on the initial side. If it starts out not spinning, then it ends up on the final side, it ends up over on this side. But the kinetic energy of rotation has to be taken into consideration if something is spinning. All right, let's talk about torque. Now, torque is just like force. Remember force? We came about force because we said, okay, we know how things move. They move because they get accelerated. That was what changes the velocity, and the force causes that acceleration. Same thing with a torque. Is like, oh, we got something rotating. Well, how did it start rotating? Well, you say it's a force, but it's not just a force because it depends on where the force is applied. If you can imagine, we have a door. So this is my door here. And the hinges are on this side. So it's going to rotate around this, rotate this way. If you're going to open the door, how are you going to open the door? Well, it depends on you apply a force, but it depends on where you apply the force, how well the door opens. So if it's rotating over here, if I tried to apply a force straight into the door, it's not going to rotate it at all. If I apply a force this way, it'll have no torque. Yeah? And if I apply a force on the outside of the door, it's going to have more torque than on the inside. Its ability to rotate is a lot more than it is on the inside. That's why we put the door handle out here furthest from the hinges. So it's easiest to open the door. If you try to open up in here, you can do it, but you have to apply really strong force. And so where you apply the force determines what your torque is. So we write torque as a script. It's actually technically a tau, a script t. It's like a lowercase t. And it is equal to the force cross the distance from the rotation axis. And careful, this is not multiply. This means this is what's called a cross product because these are both vectors. Torque is vectors too. And this is called a cross product. We already learned about a dot product when we were talking about work. And now the other one you can have is what's called a cross product. What that means is you can take the magnitude of the force times the distance it is from the rotation axis times the sine of the angle in between. So, what's that means? Well, let's look at something like from a top view of our door here. So this is our door. The rotation point is over here. Or the rotation axis is this way coming up out of the board. If I apply my force, and I apply a force at an angle like here, so here's my force right here. So my force is right here. So when I want to figure out how much torque I've done, what I have to do is I have to figure out the distance it is from the rotation axis. So I'm going to take that distance there, that's d, the distance it is away, times the force. then times the sine of the angle in between the two. Okay. Now you say, well, how are you going to do it? Are you going to do it that way, or are you going to do it this way? Well, the good thing is that sine is symmetric, about 90 degrees. So whether you do that one or that one, you're going to get the same answer. So it doesn't really matter. You just got to be careful how to do it. Just don't pick a different angle, but it's always the angle between the distance, or the displacement distance. It's really the distance. The radius vector is technically what it is. From the rotation point to where the force is applied, it's the angle between those. That is the sine of the vector. And usually you would write it like this. You would draw the radius vector. And in this case, instead of the force being here, or the distance vector, should be consistent since it's d here. Then you take the tail of the force and you plug it in at the end. So if the force is going this way, it's this angle here, with the force placed so its tail is at the end of the distance vector. That's how you calculate what torque is. Standard notation is if the rotation is counterclockwise rotation, it's positive. We talked about this before. So if the force times the radius is trying to make it spin counterclockwise, we put the torque as positive. It has a positive. If it's going clockwise, it's negative, which means it's going that way. So if you have a whole bunch of torques, you have to put them in as either positive or negative torques to sum them together. So if you have a lot of forces acting on an object, you get what's called the net force, and you have to add up the sum of all the torques. And there could be, and there'll be positive and negative torques depending on which way it makes it spin. We know from Newton's second law, remember Newton's second law said that the net force is equal to the mass times the acceleration of the object. Well, what's that have to deal with in rotation? Well, in rotation, you don't do the force, you do the net torque. So you have to sum up all the torques on an object. And then it's not going to be the mass times the acceleration because it's not moving in a line, it's going to rotate. So the net torque, by Newton's second law, is equal to I, because m is replaced with I, the distribution of the mass, times alpha. Remember, alpha is the translation, or is the angular acceleration. And alpha is related to the tangential acceleration by r, where alpha is in terms of radians per second squared. So this is Newton's second law for torque. All right. So whenever you're calculating these torque problems, you're going to have to total up the number, all the torques, and then if you know I, you can solve it for alpha. Or vice versa, if you know alpha and I, you can solve for the torques, or any combination thereof. Just remember, you have to sum the torques together, but you have to be careful about putting them in positive or negative, depending on which way the rotation is concerned. All right, so let's do these problems. Problems 9, 20, 27, 72, and 74. They talk about energy, rotation energy, and torque. And we'll get used to that, and then we'll add some more to chapter 12 after that.